In this experiment, you will study the effects of concentration and temperature changes on two reactions. Note that in each reaction there is one reactant and one product that are very different in color. The cobalt reactant in the first reaction is a dark wine red, whereas the cobalt product in this reaction is a dark violet. The iron reactant in the second reaction is yellow, while the iron product that's formed is a red-orange. The overall color of each reaction mixture will provide an excellent visual indication of how a change in concentration or temperature is affecting the concentrations of reactants and products in each equilibrium. Henry Le Chatelier concluded that when a change is imposed on a system in equilibrium, the system reacts in the direction to reduce the effect of this change. So, when does equilibrium occur? For a chemical reaction, equilibrium means that both reactants and products are present, that the reaction is a two-way street, and that the reactants are formed at the same rate as products. A reaction at equilibrium is one that is reversible, where the rate of the forward reaction equals the rate of the reverse reaction. Since the forward and reverse rates are equal, there is no net change in the concentration of reactants and products. The most common factors which affect a reaction at equilibrium are changes in the concentration of products or reactants, changes in the temperature of a reaction, or a change in the pressure exerted on a reaction. Consider the following reaction that is at equilibrium, where copper ion is reacting with 4 ammonia molecules to form a copper-amine complex. But we could also say that the copper-amine complex is reacting to form copper ions and ammonia molecules, since both the forward and reverse reactions are occurring. This equilibrium may be defined mathematically by a value called the equilibrium constant KEQ. Note that the product appears in the numerator, reactants in the denominator, and any exponents are derived from the coefficients of the balanced equation. The value for this equilibrium constant is 1.08 times 10 to the 12th, a very large number indeed. This number is constant at a given temperature, although the actual concentrations of the reactants and products can vary immensely by subjecting this reaction to different stresses. A similarly defined value called the concentration quotient Q represents the reaction when it is not at equilibrium. So, the forward and reverse reaction rates are not equal, and the reaction is still adjusting to an applied stress. Let's consider how some typical chemical stresses can affect this reaction at equilibrium. For example, if we rapidly dissolve solid copper chloride, CuCl2, in this reaction solution, the copper ion Cu2+ is increased. The equilibrium adjusts by shifting to the right, and some of the added Cu2+ reacts with NH3 to form more copper-amine product. Concentrations continue to change until the forward and reverse reaction are equal and the numerical value of the equilibrium constant KEQ is reached. If solid sodium phosphate is rapidly dissolved in the reaction solution, the Cu2+ ion is removed from the reaction by precipitating as copper phosphate. Hence, it can no longer react with NH3. The reaction shifts to the left, reducing the concentration of copper-amine complex and forming copper ion and ammonia. Finally, by increasing the temperature of this endothermic reaction, the reaction shifts to the right, and copper ion and ammonia react to form copper-amine complex. In this last case, the numerical value of the equilibrium constant KEQ also changes. Reactions are coupled if one chemical species appears in both chemical reactions. Consider the dissolving of the relatively insoluble orange salt HgI2 to form mercury ions and iodide ions. We could dissolve more HgI2 by introducing a second reaction that reacts with either the mercury or iodide ion. For example, if a solution of NaI is added, the iodide ion from this salt will react with Hg2+ ion to form the Hg4 2- complex, which is very stable. The ion that couples these two reactions is the mercury ion. Since the second reaction favors the products, it reacts with large amounts of Hg2+. But that means that more solid HgI2 in the first reaction must dissolve to provide the H2+ ion in the second one. The net result is that most of the arranged HgI2 solid dissolves due to the coupling of these two reactions through the Hg2+ ion. An acid-base indicator is also an example of a coupled reaction. For example, when phenolphthalein is dissolved in water, it ionizes by forming a -2 anion and losing 2 protons, which form hydronium ions. This equilibrium is very sensitive to changes in solution pH. For example, the second equilibrium shows what happens when hydroxide ion, or OH-, is added to a solution containing this indicator. The OH- reacts with H3O+ formed in the phenolphthalein equilibrium, shifting this equilibrium to the right, and turning the solution pink due to the increase in concentration of the -2 phenolphthalein anion. On the other hand, by adding H3O+ to a solution containing the indicator equilibrium shifts left due to an increase in the H3O+ concentration, and the reaction mixture turns colorless. Now let's see how this actually appears in lab. Several drops of phenolphthalein solution has been added to about 20 ml of water in this flask. The solution is stirred magnetically to ensure adequate mixing of any added reagents. Let's initially add a small amount of the base sodium hydroxide. Note that the added base reacts with the proton liberated in the phenolphthalein equilibrium, temporarily lowering its concentration, which shifts this equilibrium to the right. Now let's add some hydrochloric acid. The addition of acid increases the proton concentration in the phenolphthalein equilibrium, shifting the equilibrium to the left. Adding base once again shifts the equilibrium to the right, turning this indicator the bright pink color characteristic of a base solution. And adding acid one more time shifts the equilibrium to the left, turning the solution colorless, indicating either a neutral or acidic solution. If you have used a solubility table of inorganic salts, the general categories of soluble, slightly soluble, and insoluble may have been used to describe the solubility of each anion with different cations. There is a special equilibrium constant that is used to quantify the solubility of salts that are not very soluble in water. For example, consider the precipitation of the salt PbSO4, which is formed by adding a solution of PbNO3 taken twice to a solution of Na2SO4. The net ionic equation for the formation of this white salt is shown below. Reversing this equation represents the dissolving of PbSO4, forming Pb2+ ions and SO4 2- ions. The equilibrium constant for this reaction is, but since the concentration of a solid does not change and is constant, it can be combined with the equilibrium constant to form a special equilibrium constant, which is called the solubility product constant, or KSP. The KSP for PbSO4 is equal to the algebraic product of the concentrations of Pb2+ and SO4 2-. In general, the smaller the KSP, the lower the concentrations of the ions in solution and the less soluble the salt. The larger the KSP, the more soluble the salt. Comparing the KSPs of two different salts allows you to compare their solubilities in water. Consider the KSPs for PbSO4 and PbI2. The KSP for PbI2 is much less than the KSP for PbSO4. Hence, if both the iodide ion and the sulfate ion are competing for Pb2+ in an aqueous solution, the iodide ion wins, since it will form the less soluble solid PbI2. Remember, a smaller Ksp means a less soluble solid. One way of showing this is to initially form the white solid PbSO4 by mixing solutions of PbNO3 taken twice and Na2SO4. Although the precipitate PbSO4 forms, there is a small amount of it that dissolves to form Pb2+ and SO4 2- ions. If a solution of NaI, which is a source of I-, is added to the solid PbSO4, the I- will react with any Pb2+ that is in solution, forming the less soluble yellow solid PbI2. This continues until all of the PbSO4 has dissolved and only solid PbI2 is present. These reactions are coupled through the Pb2+ ion. This experiment is completed individually. Normal safety precautions include wearing of goggles, lab coat, closed-toe shoes, and gloves. A common water bath is provided if any reaction solution needs to be heated. Any acid or base spill is neutralized using sodium bicarbonate.